All right, folks, we're going to talk about Chapter 3, Section 3, which is on increasing and decreasing functions as well as using the first derivative test. The title says optimal values behind me, but it was a typo, so oops. Anyway, look at the warm-up program. I'm just going to kind of go over it with you real quick to determine the critical numbers. Remember, to determine the critical numbers of the function, you just derive it, and you end up with 3x squared minus 4x minus 4, which when you factor it, you get 3x plus 2 times x minus 2, which gives us x values of negative 2/3 and positive 2. So with my bounds, which are negative 5 and positive 5, they weren't listed in the original document that I posted on Canvas, but they're on this one. So that is a little typo I forgot to put on there as well. So the bounds are negative 5 and positive 5. When you plug in your x values into the function, you get negative 148 for negative 5, 8.45 for negative 2/3, and negative 1 for 2, and 62 for 5, which gives you a relative minimum at x equals negative 5 and a relative maximum at x equals 5, because those are the values on that given interval. Now, remember, things might change depending on the intervals, and you're going to see here in just a moment. Now, when we change the intervals from negative 3 to positive 3, my relative minimum still ends up being negative 3, but this time the relative maximum, because it's the highest, is at negative 2/3, which is 8.45. And then if I change the intervals again, this time to negative 1 and positive 1, where they're open dots at negative 1 and positive 1, you'll see that the positive 2 here doesn't even work because it's not in the interval. So even though it's a critical number of the function, since it does not work in the interval, we can't use it. And then we got negative 1 for 8. And even though negative 1 is the lowest value, because it is not open, it is not closed, we can't use it. So this time there is no relative minimum. And I meant to actually say that at positive 1 there. So let me fix that real quick. Because it's open. There we go. All right. So we do have a relative maximum. We just don't have a relative minimum because it is an open dot. Okay, now let's look at the overview. Much of calculus, as you know, is determining the behavior of a function on a given interval. We seek to know that it has a minimum or maximum value. We also want to know whether the graph is increasing or decreasing, and this chapter gives us the tools necessary to find those answers. All right, now, if a function's increasing on the interval from x of 1 to x of 2, then that means that f of x sub 1 is less than f of x sub 2. Does that not make a whole lot of sense? I understand. Here's what it means right there. That's what it means. From x sub 1 to x sub 2, this value is less than that value, which is exactly what we want. Now, also note that f prime of x is going to be greater than 0. So the derivative is going to be greater than 0. We'll talk more about that in this chapter. Now, if it's decreasing, x sub 1 if x sub 1 is less than x sub 2, then that means that the function of x sub 1 right here is greater than the function of x sub 2, which is right down there. So that means that the derivative of f of x is going to be negative or less than 0. Now, of course, if the derivative is 0, then you know it's a constant. That means it's not going to change. Because as we talked about in class, when you're measuring an instantaneous rate of change and the function's a constant, then that means that there is no change, so the derivative has to be 0. All right, so now let's talk about increasing and decreasing functions. If f, and this is the theorem, and I'm going to highlight some key components. Let f be a function that is continuous on a closed interval and differentiable on the open interval. If f prime of x is greater than 0, then the function is increasing. So I'm going to highlight that. If f prime of x is greater than 0, then the function is increasing. If f prime of x is less than 0, then the function is decreasing. And if f prime of x, y'all know I like pink because that's my daughter's favorite color. If f prime of x is equal to 0, then the f is constant, and that means it's flat. All right, so if we look right here, the function is x to the third, f of x equals x to the third minus 3 over 2x squared. And we want to find the intervals for which it is increasing or decreasing. So we determine the critical numbers by determining f prime of x, which ends up being 3x squared minus 3x. We set that equal to 0. We got 3x times x minus 1. We solve and we get x equals 0 from right here and x equals 1 from right there. So our critical numbers are 0 and 1. Now there's no bounds on here, so that means it's an open interval throughout the entire domain. So that means that we go from negative infinity to 0, our first critical number, from 0 to our next critical number, 1, and then finally from 1 to infinity. Now, we're going to need to test a value in that interval. So you can pick any value that's less than 0, and we decided to pick -1. You can use any number that you want that's less than 0, but I chose -1. Choose an easy one. So then I plug in f prime of -1, plug in -1 into the derivative right here. So f prime of -1. It ends up giving me a value of 6, which is greater than 0. So that's telling me that it's increasing on the function. Now, if I do the same, now on the interval from 0 to 1, I choose a number between. I choose 1/2. I could choose anything I want. I just choose 1/2. Make it easy for yourself. So f prime of 1/2 is going to end up giving us -3/4, which is less than 0. So that means that the function is decreasing. So f prime of 1/2 is less than 0. That means it's decreasing. And then the last one, from 1 to infinity, I chose +2. It's on the interval. Choose an easy number. Plug it in to f. So f prime of 2, when I plug it in here, is going to give me a value of 6, which is positive. So therefore, it is an increasing function. So if the derivative at your test value is positive, the function's increasing. If the derivative is negative, then that means it's decreasing. And if it's 0, then that means it's just a flat curve. So, all right. All right. I made the mistake of not saving these earlier, so that's why I'm doing it right now. Okay. Now, guidelines for finding intervals on which the function is increasing or decreasing. First, let f be continuous on the interval. To find open intervals which are increasing or decreasing, locate the critical numbers and use these numbers to determine your test intervals. Then, determine the sign of the function of f prime by picking a test value in each of the intervals. Make it easy for yourself. Don't pick something complicated. Just pick something that's in between. Like if you can use 1 or -1, use those. If 0's in the interval, use 0. Just something that's easy. And then use the theorem for increasing or decreasing function to determine whether the function decreases. All right. Now, a function is strictly monotonic on the interval if it is either increasing on the entire interval or decreasing on the entire interval. Basically, if it increases throughout, it's monotonic. If it's decreasing, it's monotonic. So that means it doesn't change. All right. Now, here's some other critical information. Using the first derivative test, let C be a critical number. What we're going to do here is we're going to use that first derivative test to determine whether that critical number is a maximum or a minimum. So, here's what you need to know. If f prime changes from negative to positive, at a particular critical number, then that is a relative minimum. So right here is an example of a relative minimum. It goes from decreasing to increasing at that critical number. If f prime changes from positive to negative, like you see here, then that's an example of a relative maximum. Now, third, if f prime does not change, then f is neither a relative minimum nor a relative maximum. As you can see here, it's increasing, and then there it's increasing. Basically, what happens is the curve flattens and it goes up. So it's not a maximum, nor is it a minimum. And the same thing goes right down there. So basically, if it changes from decreasing to increasing, you got a relative minimum. If it goes from increasing to decreasing, that's an example of a relative maximum. All right, I'm going to pause this and we're going to go to part 2. So that's the conclusion of part 1. And I'll see you with part 2.